In this video, we're going to introduce the concept of the elastic properties of solids. And generally, so one of the basic property of materials is a very useful quantity. It's called the elastic modulus. And basically, the elastic modulus is just defined as the stress divided by the strain. So if you think about it, so there's three types of elastic moduli. So the first one is called the Young's modulus. Now the Young's modulus measures the resistance of a solid to a change in its length. So this is the one that we're going to be mostly interested in. So it gives me the resistance of a solid to a change in its length. Now there is a different type of modulus called shear modulus. Now this simply measures the resistance to motion of the planes within a solid that are parallel to each other. And then finally there is one more that is called the bulk modulus. And this measures the resistance of solid to liquids to changes in their volumes. So these are all very useful quantities for especially for those of you that are in mechanical engineering. When you study the properties of solids, one of the most important quantity that you're going to be looking at is called the elastic modulus. Now in this video, we're just going to focus on one type, and this is called the Young's modulus. But once we understand how to use the Young modulus, then we can apply the same concepts to the shear modulus and the bulk modulus. So again, the definition is that the elastic modulus is the stress divided by the strain. Now, so let's focus on the first type, that is called the Young's modulus. And so basically, the Young's modulus is simply looking at the elasticity in the length. So how easy it is for me to stretch a given material is called the Young's modulus. Now, so if you look at this example right here, so what you see on this picture is an example of what is called the stress test in mechanical engineering. So in mechanical engineering, this is an example of the stress test. So suppose that you have so if you look at this bar, so this is like, so this is a bar that has a length Li. So Li is the initial length, and it has an area that is given by A. So A is called the cross-sectional area, is the area of this cross-section right here. Now, when we apply a force, so notice that the force is applied such that it's pointing in the x direction. So when I apply a force, then this bar is going to stretch by some amount called delta L. So again, notice that we have these four quantities right here. So we have Li, which is the initial length. We have delta L, which is called the extension. We have A, which is the cross-sectional area, and we have the applied force. So generally, you can see that the stress, so stress by definition is just the applied force divided by the area, and strain is the change in length divided by the initial length. So the symbol for the Young's modulus is Y, and is given by this equation right here, is the tensile stress divided by the tensile strain. So again, the tensile stress is calculated according to this equation. Is the magnitude of the force divided by the area. Meanwhile, the tensile strain is given by the change in length divided by the initial length. So this value tells me the how I can calculate the Young's modulus for any given material. So give me any material, I can perform a stress test. So a stress test simply means that I'm going to take this material and apply a force and simply measure by how much is this going to come to stretch in the presence of this applied force. So again, I can calculate my y value as stress over strain. Stress is just force per unit area. Strain is change in L over Li. All right. So this is a picture here that shows you a typical. So for a given solid, this is how the stress and the strain. So this is called the stress strain diagram. So you can see that on the x-axis is a plot of the strain, and on the y-axis is a plot of the stress. So you can see the strain does not have any unit because it's length over length, so does not have any unit here. The stress, because the stress is given in force per unit area, this is expressed in units of Newton per meter square, but in this particular example is given in meganewtons per meter square. So 1 meganewton is simply a million, or 10 to the power 6 newtons. All right. So now, so basically, so most materials are going to have a stress strain diagram that is going to look something like this. So you can see that you have, so from this point here up to this point, you can see that the stress and the strain, they vary in a linear, so the relationship between the stress and the strain is just a straight line. So this region here is called the elastic behavior. So the elastic behavior means that as soon as I remove the stress acting on the system is just going to go back to that original length. So once you remove the stress, it returns back to its original length. Now, beyond this point, so this point right here is called the elastic limit. So the elastic limit means that is the value of the stress beyond which the material is no longer elastic. So you can see that in this example right here, that value is about 350. So this is almost like 350 right here. So 350 meganewton per meter square for this given material right here in this picture is called the maximum value of the stress. So it means that if I were to apply any stress that is above the maximum stress, then I'm going to exceed my elastic limit. Now, if you keep applying more and more stress to the system, then at some point it's going to get to the breaking point. Now, at the breaking point, so for example, if you look at this material, so the breaking point just a little bit above 400, but so once you get to this point here, then the material is going to break. It's going to break apart. So again, this is a very, very useful picture. So you really want to understand make sure that you understand the relationship between the strain and the stress. And again, each material is going to have a different stress-strain relationship. So for example, you can have a stress-strain relationship with things like aluminum, iron, steel, concrete, and so on. So each material would have a stress-strain relationship that would be like a little bit different. Now this table here gives you, for example, so these are some very important quantities here, but again, as I said, I'm just going to focus on one of these. So we'll just focus on the Young's modulus. So the Young's modulus, again, this tells me the stress, tensile stress, divided by the tensile strain. So you can see some of the values for different materials. So for example, you can see that the tensile stress, the Young's modulus for steel is about 20 times 10 to the power 10. The Young's modulus for copper is about 11 times 10 to the power 10. Aluminum is about 7.0 times 10 to the power 10. Glass is about, it ranges from 6.7 to 7.8 times 10 to the power 10. So different materials have different values for the Young's modulus. So basically, the reason why this is very important is because if I know what the Young's modulus is, then I can calculate, for example, what amount of stress is needed to produce a given amount of extension. So these values here are very, very useful. So if I give you the Young's modulus, if you know what the Young's modulus is, then you can use that value to calculate the stress. So because we know that Young's modulus is equals to stress over strain, so if you know Young's modulus and the strain, you can use it to calculate the stress on the system.